Uh, Morning, everyone. Today, we are going to be making soap. We're going to be looking at a reaction known as saponification. Saponification is just the process of making soap. In chemical terminology, saponification is basically a base hydrolysis reaction for ester. So when you hydrolyze an ester, you hydrolyze an ester, you get a carboxylic acid and an alcohol. So basically that's what you'll be doing today. Also known as saponification, also used to make soap. So today you'll be aiming to learn the base catalyzed ester hydrolysis mechanism, saponification. You're going to be doing qualitative tests to compare your soaps to detergents and and commercial soap. You would also have to explain the mechanism of soap scum formation from acid-base perspective. Okay, so introduction. So soap is basically something we use for cleaning, right? And the way soap actually does its work to remove stains is that it forms something known as micelles in water, okay? So it forms something known as micelles. A micelle is basically a small sphere of aggregated soap molecule surrounding a non-polar grease molecules in water. As you can see, I'm just reading from this, but let me explain what I mean. So basically your soap looks like this. If you look at the figure below, figure 1A, you'd see your soap actually looks like this. So the soap molecule would normally have a long hydrocarbon chain, so just an alkyl chain that's non-polar, okay? And it's going to have a head that's very polar, usually ionic. So you're looking at a molecule that's either non-polar or polar, but basically has the characteristics of a non-polar molecule and a polar molecule. A non-polar long hydrophobic tail, hydrophobic in the sense that, it doesn't dissolve in water because it's non-polar, and an hydrophilic head that's usually ionic. So generally, they would normally call soap molecules, instead of calling them lipophilic or hydrophilic, generally people call them amphiphilic because, they can dissolve both in water and in oil and, thereabout. So a soap molecule looks like this, long hydrocarbon chain and, the ionic head. And then when it interacts with an oil droplet in water, oil doesn't mix with water. And when you're trying to remove stains, you're generally trying to remove something that would not dissolve in water, using your soap to remove that. So let's say you're trying to remove oil droplet from a cloth, for example, and the oil droplet looks like, this really faded spherical or circular object you're looking at right now. Now, because the oil is non-polar, the tails of the molecule of the soap that are hydrophobic, non-polar, would aggregate and interact. As you can see a lot of soap molecules interacting with the oil droplets with the tail. And by so doing, they dissolve the oil droplet. However, the function of the head, the very polar head, is to interact with water. So that means that the head allows the entire molecule, the entire aggregate, to be soluble in water, while the tail interacts with the non-polar oil droplet such that, eventually everything gets soluble in water. So if you have a oil droplet on your clothes, you put your clothes in just normal water, because you don't have soap in your water, it's not going to be clean. But if you have soap in your water, you have a non-polar component. The non-polar component of the soap will interact with the oil droplet, and by so doing, dissolve the stain on your shirt or on your plates, will dissolve it in water. By so doing, you clean your clothes, you clean your plates and what have you. So always take note of this. The reason why soap can actually, or soap or even detergents can perform their cleaning function is because they are amphiphilic. They have the hydrophobic tail that helps you remove stain, and they have the ionic head, very polar head, that helps everything dissolve in water, including those stains. Okay. All right. So now there is also something known as, the scum, soap scum, that's usually formed when, you're trying to wash something, or you generally see soap scum, in your bathtub after a long period of time. So soap scum forms as a result of the interaction of your soap molecules with the calcium or magnesiums that's found in the water. If you're living on a farm, for example, some of your water might not be filtered, so you might have a high concentration of potassium or magnesium in there, and that way you form more soap scum. Okay, and water that has a very high concentration of these ions, calcium ion and magnesium ion, from limestone deposit underground, those water are usually known as hard water. And water that has a very low concentration or no concentration of these ions are known as soft water. So soap can actually interact with hard water, okay? And that's because the soap is interacting with the calcium and the magnesium in the water. So if you are trying to clean something with hard water, it's not going to clean well as opposed to if you were using soft water, because if you're using the same amount of soap, the soap will end up interacting with the calcium and magnesium in the hard water. Okay, so you would need way more soap to be able to clean whatever you want to clean, because some of the soap would form the scum and then the other one we used to clean. So whenever you're using hard water with soap, you always form scum, and that scum is basically the aggregation of your calcium ion and magnesium ion interacting with the carboxylic acids, of the soap molecules. I'm going to explain where I came across those carboxylic acids soon. Let me see. Okay, maybe when we get to the synthesis, I will explain what I mean. So, yeah. So you want to know the difference between hard water and soft water and how it affects, cleaning generally, okay? Hard water has a high concentration of calcium and magnesium that allows the soap to form scum, which doesn't help your cleaning endeavors, whereas soft water doesn't. Okay, people have developed an alternative to overcome, hard water and be able to clean, and that's how detergents were actually created. I'm going to shed more light on that later on. So the synthesis of soap. So basically, soap is usually synthesized from triglycerides, or or fat, basically. Okay, and because these triglycerides are esters, I'm gonna share a screen right now so you guys can see what I'm talking about. Okay, so this is an example of a triglyceride. If you've taken a introductory biology class or biochemistry class, or a chemistry class that has an emphasis on biology, you would have seen the structure of triglycerides. This is what they look like. As you can see, they are esters. You can notice the ester functionalities present there. And basically, to form your soap, you're going to hydrolyze these esters into carboxylic acids and alcohols, okay? And generally, when you're doing hydrolysis of esters, you can either use an acid or base. If you want to form soap, you always have to use a base to do your hydrolysis. In this case, we're using 3 equivalents of potassium hydroxide, which is a very strong base. And the reason why we have 3 equivalents is because we have 3 ester groups on the 1 mole of your triglycerides. the end of the day, you end up cleaving at this position, and then you end up forming your carboxylate salt, which is also known as soap. If you were using an acid, you will only form a carboxylic acid right here. But because you're using a base to do the hydrolysis, you end up forming a carboxylate salt, also known as what? Soap. If you were using, if your R group is a very short chain R group, you're not going to be forming soap. You'll just be forming a carboxylate. However, for you to be able to get a soap, your R group has to be very long. Hence the reason why we are using triglyceride. So hydrolysis of triglycerides with a strong base like potassium hydroxide, sodium hydroxide ends up giving you glycerol and a carboxylate salt, which is also known as soap. All right. You can go through the mechanism, just so you get clarity on what's actually going on. So formation of hard water, well, this is not a geology class. However, it's pretty much straightforward. Hard water is formed when, CO2 and water interact with the carbonate in the ground of your limestone, and you end up getting, calcium bicarbonate, which is also known as the component that forms your hardness. So generally, there are two types of hardness in water. You can have your temporary hardness and your permanent hardness. Okay, so temporary hardness is basically composed of calcium bicarbonate. Okay, and that's when solid calcium carbonate interacts with bicarb in water, and then you end up getting calcium bicarbonate. Okay, and calcium bicarbonate, which is the main component of temporary hardness in water, can be removed by boiling, because when you boil, you end up forming carbonic acids, which decompose spontaneously into water and CO2 over time. Okay, so to get rid of temporary hardness, all you just have to do is boil, or you can just raise the pH, and that helps precipitate out the calcium carbonate, and then you can filter. Okay. However, permanent hardness is as a result of entities like calcium chloride, which cannot be removed by boiling. Permanent hardness can't be removed by boiling. You have to use some form of ion exchange resin to remove all the ions, and that way you get rid of the hardness. Okay, so again, how is soap scum formed? Now, remember when I was saying that in your hard water, you have a high concentration. It doesn't matter whether it's temporary or permanent now. When a water is hard, there is a high concentration of calcium ion and magnesium ion in the water. And those ions are known as hard acids, okay? Hard acids. And in this case, when I'm saying acids, I'm just talking about the shape of your molecule and how the electrons interact with the nucleus. It's different from the definition of acid base you're familiar with in the past. So acids are basically cations that are very small, and they have a very small shell technically. So anyway, let's go with that for now. I don't know how to explain this so that I don't waste any time. Anyway, so your calcium and your magnesium are hard acids. There are soft acids. Soft acids are basically, atoms or molecules that are positively charged, and they usually have a big size. But hard acids are usually cations that are, usually of small size, usually, calcium ions, sodium ions, magnesium ions, basically all those metals, after they've lost their electrons, they will generally form hard acids. And generally, the rule for hard soft acid theory is basically that hard acid would interact with hard bases to form very strong bonds. Soft bases would interact with soft acids to form very strong intermolecular forces of attraction. However, if you have a hard acid and a soft base, the interaction is not going to be as strong, and vice versa. Okay. Now, the ions that are present in your hard water are known as hard acids. And when you are making your soap, your carboxylic acid, your carboxylate that forms as a result of your, saponification, the carboxylate functional group is negative, that's negatively charged. That carboxylate functional group is a hard base. Okay. And the hard base of your soap can interact with the hard acid consist of the magnesium and the calcium ions in your water to form your soap scum. Okay, so soap can interact with the calcium and the magnesium in your water to form scum, and that's because the soap, which consists of a carboxylate that's a hard base, interacts with the hard acids of your cations and your cations in the water. Okay, so so over time, if you have a bathtub or something and you live in a farm or something like that, you probably are more likely to be exposed to more hard water, and then over time scum is going to form in your sink, which is usually pretty disgusting. And to overcome the issue of formation of scum, detergents were created to do that. And that's because the anions, the negatively charged add groups or positively charged add groups on detergents are usually soft. So they don't form scum readily. So that means that you can, if you were to take a soap and a detergent pound for pound, the detergent will be able to carry out more cleaning compared to the soap. And that's because the detergent has soft anions or cations on it that doesn't allow for scum formation in hard water. Okay, so generally there are three types of detergents. You have anionic detergents, which is usually what's most common in your Tide pods and things you use for cleaning your clothes. And they usually have this sulfate group that's very large. And remember when I was saying that the bigger a particular negatively charged species, the softer it becomes. So this is an example of a soft base. Okay, you can also find this particular compound in your shampoo, shaving foams, and other cleaning agents. You can also have cationic detergents, and these ones are usually found in your disinfectants and things like Lysol and antiseptics. And as you can see, the size is very big, unlike magnesium and lithium ions and sodium ions that are usually very small. You can see that this is a pretty bulky cationic group. So this is a soft acid. You can also have non-anionic detergents, and basically these guys are usually found in your dishwashing soap. If you know very well, dishwashing soap, you generally need like a tiny amount to be able to clean. And that's because that particular charged species that you would normally found on regular soap is not even present there. So you can't even form scum at all, okay? So basically that's the breakdown of how your soap works. So today you guys are going to be making soap, and just make sure you take your quiz. What else? And if you look at the procedure, there are videos, 3 general demos you might need to watch before you carry out your technique. But other than that, the experiment should be pretty straightforward and pretty practical. What else? Yeah. And of course, for your test, you're going to be testing detergents versus your soap solution, and, just to be able to see what scum means. And, how your soap is going to form more scum compared to your detergent. Okay, and that way you understand the hard soft acid base interaction theory better. All right, well, that's all we have for today. Good luck, guys.